Good morning, students. Today I'll be talking about the control of cardiovascular system. You all know what is the basic function of the cardiovascular system, isn't it? Cardiovascular system is basically consisting of the heart and the blood vessels. Heart, which is pumping the blood into the different blood vessels. All right, carrying the oxygenated blood to tissues, supplying tissue with fresh oxygen and then of course nutrients as well also. And then of course the waste material is carried back to the heart, and from the heart it's pumped to the lung, isn't it, where the blood is again refreshed. Okay, so basically it's about controlling the flow of the blood, which is a vehicle for the carriage of oxygen mainly, and of course other things like so many other things like nutrients, like hormones, and so on and so forth. Okay, so in order that the blood flows from the heart to the peripheral blood vessels, all right, the heart needs to create a kind of a pressure. Okay, so the heart is basically to creates a kind of pressure that helps in the drive of the blood from the one part of the body to the other part of the body. Okay, so here the pressure that is being created is you know the pressure difference between the heart and the peripheral blood vessels. Okay, and again you see a pressure difference between the peripheral blood vessels and the heart on the venous sites as well. Venous site as well. We have the arterial site and the venous site. Okay, and basically all this is created to circulate the blood from the heart to the various part of the body, and then various part of the body back to the heart, and then from the heart into the pulmonary circulatory system. Okay, so therefore the heart needs to the function of the heart is basically to create a kind of a output that we call as a cardiac output. All right, and cardiac output is nothing but the volume of blood that is pumped per minute by each ventricle. Okay, so the cardiac output is actually determined by two factors. One is the stroke volume and the other is heart rate. And stroke volume is nothing but it's the amount of blood that is being pumped, or rather the volume of blood that is being pumped per beat. Every beat of the heart, the volume that is being pumped, that is called as the stroke volume. So cardiac output is therefore a multiple of two things. One is the stroke volume and the heart rate. Okay, heart rate is nothing but the beating of the heart per minute, isn't it? Or what we can say is a contraction of the heart per minute. Okay, so when you take a multiple of these two, stroke volume and heart rate, you get the cardiac output. Clear? And you can see here that the heart rate, the stroke volume, they are again under control of so many other factors. These are the things that you can read yourself. Cardiac rate, for the example of the heart rate, is controlled by the sympathetic and parasympathetic drives. It is coming from the neural control that are present in the medulla, and of course you have peripheral controls as well in the form of reflexes, which these are the things that I will be talking today. But anyway, cardiac rate is controlled by these factors, and when you look at stroke volume, you'll find that even the sympathetic actually discharge is helping in the formation of or development of an adequate stroke volume. Okay, uh, by by contributing to the strength of contraction of the heart. So with an increase force of contraction, there would be an increase volume that can be pumped out of the heart in per beat. Okay, or what we call as stroke volume. So therefore the sympathetic drive is something that controls not only the rate of the heart, but then it also controls the ability to pump, which is a stroke volume of the heart. Okay, and of course you have other things that controls the stroke volume. One is the inherent what we call is the inherent property of the heart, which is called the Frank-Starling's. See, the heart is something like a balloon. The more you stretch it, the more it has force to contract. Okay, so this law, which states that the initial length of the fiber is proportional to the force of contraction is called as the Frank-Starling's law, and we call this factor as the Frank-Starling's factor. Okay, it determines the it determines the stroke volume. Okay, so anyway, I'm not going into the details of cardiac output. Whatever I've said today about cardiac output is more than sufficient for your level. Okay, within your scope, this is more than sufficient. So if a question comes on cardiac output, you can write what is the definition of it and what are the determinants of cardiac output, which I have already highlighted in the slides here. One is the cardiac rate and the other stroke volume, and these are all factors that control these two determinants. Okay, because mean arterial pressure also controls the stroke volume by inhibiting, all right, by decreasing, all right, because we'll come to this later. I will have a separate class on this, why it has an effect on the stroke volume. Okay, but anyway, these are two determinants and these are all factors controlling. End diastolic volume is again determined by Frank-Starling's. Okay, the more the end diastolic volume, the more is the stretch in the heart, and so the more would be the force of contraction, resulting in increase. I mean, more will be the stroke volume. Clear? So if you know these, number of factors in relation to cardiac output, that will be more than sufficient at your level. Okay. So anyway, my purpose of bringing the slide here is, one is that you should know about cardiac output, and two is that cardiac output is a function of the heart. Okay. So it's a function of the heart, and the cardiac output is not something that is always constant. It's something that changes with let's say a change in posture or a change in the activity of the body, all right, and therefore cardiac output needs to be changed with the requirement or the need of the body, all right, and in order to do that, the heart needs to be regulated. Okay, so it needs to be regulated. That's why we are going to discuss control or regulation of the cardiovascular system today. Okay, and we're discussing that so that we can know that how the heart, or rather how the cardiovascular system adapts to a change in different activities, all right, and different postures in different conditions, and maintaining the demanded output, okay, cardiac output, all right, by the body. Okay, then another parameter that is important for us to discuss when we, or rather that stimulate the discussion of today's topic, the control of cardiovascular system, is the control of mean arterial pressure. Okay, the earlier slide I have shown you how how it is important to control the cardiac output, and we have seen that the cardiac output is determined by heart rate and stroke volume, and so that slide itself tells us that heart rate control is also a very important factor. Stroke volume control is also a very important factor when we talk about regulation of cardiovascular system. Okay, so when you talk of regulation of vascular system, it means the control of all these parameters: the heart rate, the stroke volume, the mean arterial pressure, because all these they will be determining the flow. All right, and the flow is what we are all the flow is what is rather the end point that determines the availability of oxygen, fresh oxygen, and nutrients, and many other things. Clear? So controlling these is essential, because man is not only positioned at rest every time, but then man is a creature that is mobile, that performs different activities, all right, and he sleeps and he wake up to perform different types of activities, and all these require a change in all these parameters. Okay, so therefore, to bring about a change in all these parameters, according to the need, all right, according to the physiological need, we need a controlling system. Okay, if you think of a human being as something that just hibernate or spend his entire life resting, then we may probably not need a controlling system. Okay, because the heart by itself probably can meet the demand of the body. There is something called as an intrinsic heart rate, where the sinoatrial node, the pacemaker that we have discussed in the earlier class, can generate a rhythm of 100 beats per minute. 100 beats per minute. If the heart pumps at 100 beats per minute, that is more than sufficient to create an output that will meet the demand of the body at rest. Understand? But as I've said, the human body does not spend its time only at rest. All right, human is a species that is mobile and therefore has different types of activities, and all these activities require different type of cardiac output, which again which is determined by a number of factors like the heart rate, stroke volume. All right, and all these then determine the flow, all right, by creating a kind of pressure which we call as the mean arterial pressure. Fine. So I think that sets the tone for what we're going to discuss today, the control of the cardiovascular system. As you can see, cardiovascular system is basically made up of the heart and the blood vessels. So control is not only the control of the control of this entire system, is the control of the heart as well as the vascular system. Okay, and when we talk of that, we are talking of a control system that is present in the brain. And which part of the brain? Something called as the medulla oblongata, which is the stem of the brain, which is called as the brain stem. Okay, brain stem, part of the brain stem. All right. So this control system is present here in the medulla oblongata. As you can see in the slide, this is the medulla oblongata, this whole thing. Okay, and you have these new group of nuclei. Okay, all right, that forms the controlling system. Okay, in some books this entire system is called as a vasomotor center. All right, vasomotor center is basically a center consisting of a cardioinhibitory center. These are shaded in light blue, or in a cardio-acceleratory center, which is shaded in the pink. All right. So these are nothing but groups of nuclei. All right. For example, let us say the cardioinhibitory center is something that is present in it is nothing but a collection of cell bodies. All right. Generally seen in the rostroventrolateral portion of the medulla. Okay, so from here, from these cell bodies, then the axons are given off, descends into the spinal cord, all right, into something called intermediolateral lateral gray horn. Okay, and all right, and then it comes out as a sympathetic fiber. And cardioacceleratory center then is another collection of neurons that results in what we call the parasympathetic flow. Okay, so cardioaccelerator center is nothing but the parasympathetic center, we can say. Cardioinhibitory center is nothing but the sympathetic center. That is, I mean, we can simplify that into that form. Okay, all right, so these are called as the neural control centers. All right, the cardioinhibitory center, the cardio-acceleratory center that are present in the medulla oblongata. You have another center that is present on the posterior medulla, or rather just posterior to these two centers. All right, there is something called as nucleus tractus arteriosus. This is also very important and plays a role in the control system. because it receives all the sensory input from the peripheral receptors. Now these peripheral receptors also play a very important role in controlling this uh, control system here. Okay, they can either switch off the sympathetic, all right, the discharge, and allow the what we call as the vagal tone to take over. Okay, or the sorry, switch off this part, the cardio acceleratory center, and then allow this part, this one shaded in blue, which is the cardioinhibitory center. This is cardioinhibitory center is nothing but the parasympathetic center. Cardio center is nothing but the sympathetic center. Okay, I think that is clear. I've corrected what I said earlier. Okay, now nucleus tractus solitarius, what does it do? It receives all sensation and then determines the which is to be activated and which is to be turned off. Okay, so I think we will stop at that for with regards to how nucleus tractus solitarius control this system. Okay, now the cardioinhibitory center, as the name suggested, what does it do? It plays a role in inhibiting. All right. So it decelerate, rather, we can say it decelerate the heart rate. Okay, and it can also, by decelerating the heart rate, therefore also decreases the cardiac output and also have an effect on the mean arterial pressure. So it can cause a fall in mean arterial pressure. Okay, so one the effect of one parameter results in the kind of cascading effect of another parameter. Okay, so if you look at activation of cardio activity center, what happens that when this is stimulated, the heart is accelerated. All right, so there would be an increased heart rate, resulting in increased cardiac output and resulting in increased arterial blood pressure. Clear? Is it clear? Now this has to be there in your mind. Okay,
Yes, sir.
clear? So this is how this medullary cardio control system, or rather control system of the heart, all right, uh, reigns on the heart, or rather controls in the heart, regulates the heart. So it can make the heart, uh, beat at an increased pace, or it can make the heart beat at a decreased pace. Okay. So when we are at rest, when we are sleeping, the heart rate is decreased, isn't it? We get something like, say, a kind of a bradycardia, we can say, at rest, bradycardia at rest. Okay. But then when we are climbing stairs, you will find that the heart rate increases. And that is because, the heart is responding to the demand. Okay. The demand for oxygen and nutrient. When you are resting, the demand is less. But when you are, climbing stairs, the demand is more, isn't it? The muscle have to, spend more oxygen to generate more energy, isn't it? So therefore, the heart needs to pump more number of times, so as to increase the cardiac output, and therefore increase the amount of, blood that can perfuse the muscle in action. Okay, clear? So it is a system that responds to demand. Okay, clear? And it is the demand that controls the system, and the system control the heart. Am I clear?
Yes, sir.
Okay, so to sum up, we can say that we have this neural control, which is an extrinsic. It's an innervation because the heart is being innervated by these two nerves, the sympathetic nerve and the parasympathetic nerve. Okay, so it's extrinsic because it's outside the heart. As I've said earlier, you have an intrinsic mechanism as well that you know helps in the contraction of the heart. Okay, and that is generated from the SA node. All right, but then you have this extrinsic control system. all right, that modulate, rather, manipulates the heart, the parameters, of the heart, okay, by modulating them, okay. So it can increase heart rate, increase cardiac output, or decrease heart rate, decrease cardiac output. And when you increase cardiac output, that would have an effect on the arterial pressure as well, okay. So to sum up, therefore, control is partly autonomic nervous system and of course neural, which is coming from the brainstem because of the presence of these collection of neurons that we call as the vasomotor center. And the vasomotor center, which is present in the medulla oblongata, is basically made up of two, centers. One is the cardioacceleratory center, and the other is the cardioinhibitory center. Okay, cardioacceleratory center results in the, give rise to the sympathetic innervation of the heart. Okay, and cardioinhibitory center give rise to the vagus nerve that again innervates the heart and decelerates the heart. Okay, clear? Okay, so what we have seen so far, we have seen that the heart is being controlled. First of all, there is an intrinsic control, and two is the extrinsic control, which is present in the medulla oblongata, okay, giving rise to sympathetic and parasympathetic innervation of the heart. Okay, now besides the, these neural control, the central control, that we can call the neural control, we have the peripheral control as well, all right. And these are all receptors that are present in the heart, are present in the blood vessels, okay. And they also play a role in modulating, the activity of the heart, or rather the function of the cardiovascular system as a whole. Understand that too, these again these controlling factors that are present in the periphery are again, based on demand, all right. They depend on the demand. So if there is a demand of flow, to decrease the flow or to increase the flow, let us say, or if there is a demand to either increase the concentration of the gases, it may be oxygen, all right, concentration that needs to be regulated. So they do so by regulating the cardiovascular system, okay, because cardiovascular system would also drive the, if you take into consideration the concentration of oxygen, let's say, is actually the, the heart that is, driving the oxygenation of the blood, okay. That therefore finally, or rather eventually changes the concentration of oxygen in the blood, okay. So it drives the blood from the right ventricle into the pulmonary system, into the lungs, where it is oxygenated, and then that is again pumped into the peripheral tissue, okay, clear. So therefore we see that, the cardiovascular system as a whole itself, all right, is by itself a controlling, it plays a part, it plays a part in the controlling of itself, all right, fine, because we have receptors in the heart, we have receptors in the blood vessels, and these receptors would, respond to a number of changes. Maybe a change in the volume in the heart, or it may be a change in the, a change in the flow across the blood vessel, or it may be a change in the pressure, experienced by the blood vessels, resulting in a stretch of these receptors, okay, or maybe a change in the, the gaseous concentration of the blood itself, okay, within the cardiovascular compartment, clear. So you have all these, playing a role in controlling the neural control center, all right, and then that will have an effect on the heart and the cardiovascular system as a whole, okay. So it is a very comprehensive, network, all right. of the neural matter, all right, the neural control system which is present in the brainstem, and the peripheral, receptors which are present in the along the length of the cardiovascular system as a whole. Okay, clear. So, what are these peripheral control, system? These are called as the reflexes. Okay, we call them as the reflexes. So, one of the major reflexes is the baroreceptor reflex. Okay. Now, the name itself suggests that these are receptor responding to pressure, isn't it? Responding to pressure. Baro comes from the baro. What is that thing that barometric barometer? All right, is a thing that controls the. I mean, it's a device that measures the pressure, isn't it, in any system? Okay. So similarly, this is something like that. Baroreceptor is something like that. It measures the pressure within the vascular system. Okay. So it's a pressure within the cardiovascular system. Okay, that stimulate the baroreceptors. Okay. So if the pressure is more than normal, the normal pressure is 120 to 80. Okay. So we say 180, we say 120 by 80. 120 is the systolic pressure, 80 is the diastolic pressure. But you see the the pressure that can maintain an adequate output, or rather an adequate perfusion pressure to meet the demand of the tissue, is between 120 and 80. Okay. So anyway, if the pressure is above this 120, then that pressure could cause a stretch in the wall and a stretch of the receptors. These receptors are very similar to the Golgi tendon organs. They respond to tension in the wall. Okay, so kind of a tension receptor. So they would respond to stretch, something like the Golgi tendon organ, the muscle spindle. I don't know whether we have. I think we must have. That must have been discussed when you discuss neuromuscular system. Okay. So anyway, they are very similar to these type of receptors, and they respond to a change in the length and tension. Okay. So anyway, a change in, elevation in the arterial blood pressure would causes the stretch of these receptors, resulting in stimulation of these receptors, and then these receptors would be, generating action potential, which we call as the impulses or discharge, all right, and these would reach the vasomotor center, all right, through the nucleus tractus solitarius, which is the sensory component of the neural control system. Okay, so when it reaches the nucleus tractus solitarius, it's going to be relayed into the vasomotor system, and when it reaches when this impulse activates the nucleus tractus solitarius, that would be relate to the cardio inhibitory and the cardio excitatory centers in the vasomotor center. And what is going to happen here is that the impulse is coming from the baroreceptors, all right, discharging at high frequency impulse. Okay, they would depress the vasomotor center. I mean, they would depress the cardio excitatory center and allow the cardio inhibitory center to inhibit the cardio excitatory center as well, and allow the vagal tone to take the upper hand. Okay, so what is happening is that we have a decreased discharge of the sympathetic and an increased vagal tone. What is happening here when you have increased vagal tone? These they are going to act on this sinoatrial node, all right, decreasing the pace or the rhythm. Okay, decreasing the rhythm, fine, and resulting in a decreased heart rate. Fine. So when you decrease the heart rate, you're going to decrease the cardiac output. stroke volume, all right, and then that would result in a fall of the pressure. Okay, so as you can see here, we have this baroreceptor reflex mechanism, all right, which controls the heart, is it, through the neural control system, okay, and regulates the, or rather modulates the pressure as well as the heart rate, the cardiac output. So these are the that we have been talking from the very beginning. No, these are all cardiovascular parameters, and you know uh, eventually these are controlled by all these systems. So baroreceptor is one of the peripheral control system, okay, that can have an impact on the function of the heart, okay, and the vascular system as a whole. I'll come to the, I'll be talking about the vascular control as well, because that also plays a very important role. The vascular constriction and dilation also plays a very important role in regulating the pressure, the arterial blood pressure, okay, and therefore regulates the flow also, the perfusion pressure also to the tissue, okay. So anyway, this is baroreceptor reflex is important when we are changing posture as well. So it's something that controls the pressure on an immediate basis. All right. So when you from a lying down position, when you change your posture to sitting, and from sitting to standing, so immediate control of the reflex would be, I mean the immediate control of the cardiac parameters would be done by the baroreceptor reflex. It would, correct the pressure and ensure that the blood is distributed to the upper part of the body, which is affected by gravity. Okay, so this is done by the baroreceptor reflex. Okay, so process of baroreceptor reflex. Summarize this. It happens when there's arterial pressure which becomes elevated. So pressure can result in the change in the rate of discharge from the baroreceptor reflex, or the rate of discharge by baroreceptor reflex can be changed by different pressures. Okay, high pressure would cause increase frequency of discharge. A low pressure would decrease the frequency of discharge. Okay, clear. So both are in actuality, both are signals that is being sent to the brain. The brain can perceive as a kind of a frequency, which is either a high frequency or a low frequency, and then respond to that. Okay, so we can say that, I mean, if we take this argument into consideration, then we can say that the baroreceptor reflex does not only control or modulate the neural control system only when blood pressure is elevated, but it also modulates the neural control system even when pressure is falling. Okay, so anyway, we generally, when we talk about baroreceptor reflex, we we tend to start with the stimulation of the baroreceptors when pressure is elevated. Okay, so blood pressure becomes above normal. That would excite the receptors, all right, that are present in the carotid sinus and the aortic arch. There would be increased rate of firing, all right, and resulting increased rate of firing of the afferent nerves, the glossopharyngeal and vagus, and in the cardiovascular system, or the cardiovascular centers, will be affected. And in this case, the cardio axillary center would be depressed, the cardio inhibitory centers would be activated, all right, you can say, and resulting in a decreased sympathetic cardiac nerve activity, a decreased sympathetic vasoconstriction nerve activity, and of course an increased parasympathetic nerve activity. Now, all this would result in a number of things. One is a decreased heart rate, decreased stroke volume, because there would be a decreased force of contraction as well. and even dilation of the arteries and the veins, all right, resulting in a fall in the what it calls a total peripheral resistance. Okay, and when this happens, you will find that the combined effect on combined effect on all these parameters would result in a fall in the blood pressure. Okay, so this is a very important process to remember, and baroreceptor reflex is something that is frequently asked and that you must know in the tip of your finger. Okay, and it is a system, or rather it is a control system, or we can say a control uh, system that is immediate in nature. All right, short term, immediate in nature. So we have already seen here also that the sympathetic change in sympathetic parasympathetic would have an effect on the blood vessels. But in this next slide, I would go a little bit maybe a little bit deeper. Find that the neurocontrol of peripheral system aims to we say it aims to alter blood distribution in response to specific demands, as I've earlier said, and maintain appropriate mean arterial pressure by changing the vessel diameter. Okay, so this is the objective. When we talk of control of the vascular system, these are basically the objectives. Okay, and control again originates in the cardiac centers in the medulla. All right, they consist of the two centers of these vasomotor centers, and eventually what happens that these centers, depending on which component is activated, if it is sympathetic drive that is being increased, then you would there would be vasoconstriction of the vascular system. All right, increase discharge of noradrenaline would result in this, or if there is it can also result in, depending on what kind of impulse that is being generated, it can also cause the vasodilation. All right, and vasoconstriction, vasodilation, they would have an effect on the total peripheral vascular resistance. So you decrease the diameter by vasoconstriction, that would increase the total peripheral vascular resistance and decrease the flow, and you increase the diameter by vasodilation, that would decrease the total peripheral vascular resistance, increase the flow, as well as, of course, decrease the blood pressure, the arterial blood pressure. Okay, vasoconstriction will increase the arterial blood pressure. Okay, so as I've said, the need to control the cardiovascular system is to meet the demand. All right, like for example in exercise here. All right, we have a number of peripheral receptors that are being activated. So besides the baroreceptors, you have different peripheral receptors that can be activated at different conditions of the cardiovascular system. Okay, so it can be the baroreceptor themselves responding to a pressure. It can be proprioceptors responding to movement of the muscles, and when the muscles move, there is demand, increased demand. Or chemoreceptors are again, the receptors responding to change in the chemical concentration in the blood. Okay, so the chemical concentration can be affected by the demand. Okay, then you have other things. All right, like for example, what we call as CNS ischemic response. Again, you have these are receptors present in the brain when pressure falls very low, right? The mean arterial pressure, when the mean arterial pressure is less than 40 millimeters of mercury, then only they respond. Okay, so CNS ischemic response is another type of control mechanism. That's called as a last ditch mechanism. Then you have these atrial receptors which are present in atrium. They would respond when there's a change in the volume of the right atrium, and you can change the volume of the right atrium by infusion. right? For example, in the hospital where people are being given infusion, maybe blood transfusion or saline infusion, okay, that would cause an increase, atrial volume, and the low pressure baroreceptors which are present in the heart, like in the atrium, they would respond to that change in volume. Okay, so will result in a kind of a reflex that is called as a Bainbridge reflex. Okay, so you have number of reflexes, that respond to different kinds of situations, and eventually modulate the function of the cardiovascular system. Okay, so here in this slide, I'm just showing you how increased activity like exercise cause a change in the parameters of the heart. Okay, so if you do an exercise, there would be an increase in blood pressure, there would be an increase in muscle movement, there would be consumption of oxygen, and the release of carbon dioxide. So you have a change in the chemical concentration as well, and all these would have an effect on the medullary control system. All right, and to meet the demand, what is happening here is that the cardiac control system would result in the you know would have an effect on the sino-atrial node, and resulting according to the need, either increase heart rate or a decrease in heart rate. Okay, so when one is doing exercise, of course, there is a need to increase the heart rate. Okay, and you look at baroreceptor, because of an increased pressure, you eventually think that there would be a fall in pressure, but then you have the other receptors that overwhelm the effect of the baroreceptors. You have the chemoreceptors, the protoreceptors. So eventually, the sum up effect is that heart rate increases so as to meet the demand during the exercise. Okay, so by showing this slide, my intent is to to show that the cardiovascular system can be affected by a number of receptors at the same time, and it is actually the sum up, or what you call the summative effect of all these that eventually have the control on the cardiac control center, which is present in the medullary center, and therefore eventually change the parameters, the cardiac parameters, according to the requirement. Okay, clear? So what have we learned today? We have learned today that the cardiovascular system needs to be controlled, and it needs to be controlled because the requirement or the demand changes with activity. All right, or we can say with time, diurnal change also should be there, depending on what part of the day that we are in. We are in the night, then we are in the resting position or in sleep, and therefore the demand would be less, and the effect on the cardiovascular system would be that of resting condition, isn't it? When you are active during the day, again during the day, that the activity during the day again also would differ when you're climbing stairs, when you're running, doing your jogging, or when you're just walking to the office, or to the lecture theater. All right, or you're just doing some mild type of activity. All these would be changed, all right, by these receptors that are present in the cardiovascular system as a whole. Okay, clear? Not only the cardiovascular system, but then in the even outside the cardiovascular system, like in the muscle also. Okay, or in the joints, in the muscle, in the joints. Receptors are present in different places. Okay, so all these would have an effect on the neural control center and would modulate it, according to the which sorry affected, and then this would modulate the cardiovascular system as a whole, according to the requirement, right? According to the demand, the requirement, or the need. Okay, so the objective is to meet the needs of the body. All right, so that is why we have a regulating system. All right, now you must divide these regulating system into two. One is the neural control, and two is the peripheral control, okay, which we call as the reflexes. Fine. So your job today, I am only uh, only giving you a kind of a gist, but you need to read more. All right, and you need to do your homework and find out what are the other peripheral reflexes, all right, that uh, have an effect on the cardiovascular system. All right, I have named a number of them. I said it's CNS ischemic response. Besides baroreceptor mechanism, the proprioceptors, the chemoreceptors, I told you about Bainbridge reflex, and I told you about the CNS ischemic response. Okay, there are so many. There's a long list, but a few of these, it will be more than sufficient. Baroreceptor should be on the tip of your finger. Okay, baroreceptor reflex should be on the tip of your finger. You should know also something about chemoreceptor reflex, and of course the other small reflexes that we may need to discuss again when we talk on the control of the arterial blood pressure. I'm going to have a separate, I'm going to take a separate class on the control of arterial blood pressure. Okay, so with this in the background, I'm sure that you'll be able to, the next time we take the control of blood pressure, I think you will have a good background to understand. All right, the all the factors that control the mean arterial blood pressure. Okay, clear? Is it clear?
Yes, sir.
So do that homework I'm giving you. All right, you check your textbook and read what you've heard today. That should be registered in your mind, and you can reinforce it by reading. Am I clear?
Yes, sir.
Yes, sir.
All right. Thank you. Thank you,
Yes, sir.
and goodbye.
Thank you, sir.
Thank you.